Should we get started? Okay, next talk is Andrew Lampinen. He's going to talk about causality.
Awesome, thank you. So this is going to be a bit of a meandering talk, and so I'm not even going to try to give you an outline ahead of time. The reason for that is I want to introduce a few different themes that I think will be of interest for this workshop. Maybe we'll stimulate some useful discussion later. But the through line of the talk is, of course, going to be about language models, which a lot of people have talked about already. And in particular, I'm going to try to address this question of what could passive language modeling teach a system about experimentation and causal reasoning? And if that question doesn't fully make sense to you yet, I'm hoping to unpack it a little bit in the next couple of slides. So it starts with this observation that passive observation generally can't distinguish causal structure from correlations. And of course, everybody in this room probably knows this. But if you're just observing the world and you see that when this person is around, cars are more likely to be broken, you don't know whether that's because this person is going around breaking cars or there's some other causal structure that's leading to those things. And so as scientists, what we do is we do experiments where we intervene on the world, and that helps us to determine what's causal structure and what's just correlation. So maybe we bring a car to the mechanic and we're like, oh, he didn't break it, he actually made it start working better, and therefore we can learn something about what the causal structure of the world is. And we can formalize this, for example, as Pearl has, in terms of doing interventions in causal DAGs, where you can think of sort of the causal structures in the world as being graphs where there's some nodes with some edges between them. The nodes are sort of like abstract states of the world, and the edges are the causal effects that they have on one another. Then you can do interventions in this graph and see how they propagate to the rest of the graph to understand something about the causal structure. OK, so Pearl has articulated this causal hierarchy where at the first level, you just have pure correlative, associative learning. The next level, you have what you can learn from interventions. And at the third level, you can have counterfactuals. And because of this hierarchy, Pearl has been quite skeptical of what modern machine learning methods are actually achieving, particularly arguing that they're just at the level of association because they're just optimizing some property of the observed data. So there's a question that this raises, which is, are there any machine learning systems that intervene, that could go out there in the world and learn something about causality? And fortunately, there are. There's reinforcement learning agents, which I've worked on some in my past work, and a number of other people here have as well. And the way RL agents work is, well, imagine this robot is my reinforcement learning agent. Imagine I'm stressed preparing for this talk, so I want some ice cream. I ask my RL agent to get me some ice cream. The RL agent goes out into the world. It takes some actions. Something happens. And we see whether that was good or bad. Maybe I'm like, no, that's a plate of salad. I didn't really want that, so I give it a negative reward. Then it goes out in the world and tries something else, and it gets some ice cream. And I say, OK, yeah, that was what I was looking for. And I give it a positive reward. But the important point is that because this system is learning by taking actions in the world, it's intervening on the environment, and it's seeing what happens in response to that, it can learn about the causal structure of the world. All right, and because of this, a lot of prior work has shown that reinforcement learning agents can not only learn about causal structures, but they can even meta-learn strategies for discovering them. And what that means is that you can teach an agent how to go into a new situation with a causal structure that it's never seen before, and it can actually experiment, discover what that causal structure is, and then use that to achieve some goal in that new situation. So here's a bunch of papers on that if you're interested. And the thing I want to highlight is that it can do this without needing any sort of explicit structured DAG-like representation. It just learns something in this vector representation inside of the RL agent that lets it figure out how to experiment, determine what's going on, and then use that to achieve some goal. OK, so why am I talking about RL agents when I started off motivating this with a question about language models? Well, there's an important difference between reinforcement learning agents and language models, which is that language models don't intervene on the world during training. Instead, how you train them is that you take a bunch of text off the internet, which I'm depicting as books here instead of a bunch of computers, and then you pass that through the system, and you sort of like break it up into words or pieces of words, and then you ask them all to predict what piece of word comes next at each step in time. And this, for the machine learning aficionados in the audience, is basically just doing behavioral cloning, which is an offline method on human language. So this has led a number of people who know about these results on observation and causality to ask, are language models fundamentally limited from learning about causality because they don't intervene? This has been asked on Twitter, of course, as everything is, but also in the literature, in this Causal Parrots paper in particular. So that's interesting, but there's this other body of work showing that language models can sometimes do these sophisticated, interesting things in some cases that you would think maybe require causal understanding. So for example, language models serve as pretty good priors for certain kinds of causal inferences. And they can also do things like interact through tools and code and things that you might think of as requiring some sort of causal understanding. But of course, with any real language model, there's a bunch of questions that come up when you see these kinds of results, like, are they really doing generalizable causal reasoning, or are they just sort of parroting causal structures that they observed in training? And maybe it's because the models were fine-tuned with some reinforcement learning or something that they're actually able to learn these causal structures. So since pure language models don't intervene, at least before the RL training part, are they incapable of learning about causality? Hopefully that question makes a little more sense than when I first asked it. But the point I want to make, the first observation I want to make actually, is that passive learning doesn't necessarily imply that data are observational. And a very intuitive example of that should be if you were reading a paper, the fact that you're reading that paper doesn't mean that the data in it suddenly become observational just because you're reading it rather than doing the experiments yourself, right? There's still experimental data that you can learn about causal structures in the world from. And indeed, the internet data that these language models are learning from is full of a lot of interventions and a bunch of inferences about the results of those interventions. So for example, if you go on Stack Overflow, you can see people putting some code out there and saying, hey, I ran this code, I got these results, I ran this other code, and I got this other result. Like, why is that going on? And then someone explains it to them. Or on Wikipedia, you can see science experiments, what people did, what they found, why that was, what it tells you about the causal structure of the world. So I think that some of the prior work that's been considering what language models and other ML systems can learn about causality has been sort of conflating these two dimensions that are of the two dimensions of experience that are different. So there's this observational interventional dimension, which has been important in the causality literature. And there's also this distinction between active learning and passive learning. So in the causality literature, we know that observational data a system can't learn causal structures from. It can only learn associations. But there's also this distinction between active and passive learning, which has been more common in cognitive and neuroscience and RL versus BC. We know there's certain advantages to active learning, but we don't fully know what the implications for causality are. So for an active learning system, we've seen from a lot of prior research that scientists that can intervene and do active learning and also RL agents can learn about causal structures in the world. But language models and BC agents are down here in this other quadrant that hasn't been explored as much, where they're learning from data that may be interventional, like Stack Overflow posts, but they're doing that learning passively, where they're not out there performing the experiments themselves. They're just observing what other people have done. So the question that I want to address is, are these models actually capable of learning something generalizable about causality? OK, and what I'm going to try to argue is that there's two routes to causal understanding from passive learning. The first is learning generalizable causal strategies. So I'm going to show that these systems could learn a strategy for how to intervene, determine causal structures in the world, and then to use it that can generalize to new causal structures they've never seen in training. And the second is that they could learn from causal explanations, which can tell them about latent causal structures in the world that are not discoverable from the rest of the data alone. So to unpack that a little bit more, the idea of the learning causal strategies works like this. So of course, a system, if it wants to exploit causal structures, will need to be able to intervene at test time. So I'm not saying that the system could do without intervention at all, but like a language model that learns passively just from recorded conversations on the internet, but at test time it actually talks to the user, maybe the models could learn something where they observe the kinds of interventions that people do to perform experiments on the internet. And then at test time, they're deployed in a new setting, and they can actually use that knowledge to perform experiments for themselves and learn, just as it's been shown in prior work that reinforcement learning agents can if they train actively. The second idea about explanations is pretty straightforward. So explanations from the cognitive science literature, we think, are intended to communicate the links between some concrete situation, like a problem or an issue that someone's having, and some more generalizable causal principles that will help them in the future. So for example, you might tell someone their code isn't compiling because of some issue with their CUDA version, and that helps them to, in the future, when they run into a similar problem, solve that problem, helps them to generalize in the future. So the other question is, could explanations help agents to learn causal strategies that help them to generalize appropriately out of distribution? All right, so one last intuitive image, and then we'll get to some actual things. metaphorically, what I'm trying to ask in this talk is, could a system learn to be a scientist just by reading a bunch of textbooks about how people perform experiments and what they find, and then use that knowledge to go out and actually do some science in the world? Does that make sense? Any questions so far? Awesome. So I'm going to tell you about some experiments, starting with a simple causal DAG environment. And one of the things that we do in our work is we try to understand things about language models by stripping them down to the basics. And the reason we do that is, of course, if you experiment on a real language model, it's hard to know what's in the training data, what it could have just memorized, what it's just parroting from there. So what we do is we try to strip things down to the simple elements that we think would be necessary for simulating what goes on in the more complex language model, then see what the model is capable of learning in that context, then try to extrapolate to what the larger systems are doing. So that's what we're going to do here. We're going to create an analog to language models that's more similar to the prior work on reinforcement learning agents that learn causality. In particular, it's going to be a fairly standard agent architecture for RL or BC agents, where you have some modality-specific encoders that take in text, images, whatever the agent is seeing. You have a big old transformer memory, and then you have an action policy which outputs what the agent should do. And this is actually, if you squint at it, quite similar to a language model architecture. So basically, in a language model, you have some modality-specific encoders that are like the tokenizers and the embedding layer. Then you have a massive transformer in the middle, and then you have some action policy which decides what word to output next or word piece to output next, which is like the output embeddings in the softmax layer. So this is actually kind of a good analog for a language model, we'd argue. And we're going to train this model and test it in an environment that has some underlying latent DAG structure. So the way this works is that there's going to be some causal DAG over 5 variables, nothing too crazy complicated. And the agent is not going to be able to observe that DAG directly, the language model-like agent. It's going to instead just see the values of the variables in the environment. And it's going to be able to take actions which intervene on those variables that are going to set one variable to a particular value, and then see how that propagates to the other variables in the graph. OK, and then the way that we set this up to make this an interesting problem for the agent is that the graph is going to be resampled every episode, every few steps, so that the agent has to try to figure out in a limited time what is going on in the current causal graph. And then we're going to give it 2 phases. So first, it has some free time to experiment for a few trials. Then we give it an exploitation phase where it has to, we give it a goal to maximize, and we assess how well it's able to maximize that goal. OK, and the way that we're going to set this up to parallel a language model is we're going to train it passively with behavioral cloning on data from an expert that does sort of what the scientific experts on Wikipedia or Stack Overflow might have done. It intervenes on the variables in order to figure out what the causal structure is, what's going on. And then during exploitation, it optimally takes advantage of that to achieve its goal. And in order to make for an interesting train test generalization split, we're going to enforce some constraints on the training data. And in particular, we're going to enforce that in the training data, this node is never a parent of this node. So for example, this edge wouldn't be allowed during training because it would make D an indirect ancestor. Sorry, I should have said an ancestor, an indirect ancestor of node E. Then we're going to test the agent on its ability to actively maximize E in structures where D is either the key node to intervene on to maximize E, or it's a critical node on the path to maximizing E. And the idea is that this should pose a challenging test where we're posing, during training, the agent never sees any structure where D has any causal effect on E. And now we're putting it in test situations where D is critical to maximizing E, and we're going to see if it can handle that. And these are the results. So in yellow here, I'm showing the train performance over the course of training. In green and purple, I'm showing the test performance on 2 different test versions. And basically what you can see is that the agent is getting quite good, not only at the training tasks, but also at these held out evaluation tasks. Of course, there's a number of ways that the agent could be solving these, not all of which are causal reasoning. So we compared to several heuristics and several correlational methods the agent could be using to compute this. Not going to go into all the details of that. But basically, the gold bar is showing how much of the time the agent's actions match the optimal causal expert policy. The green and purple bars are how much it matches the heuristics and the correlational statistics. Basically, what you can see is, especially in the test distributions, the agent is behaving more like the correlational policy, more like the causal expert than the correlational or heuristic policies. So that's great. it seems like, at least in this setting, agents can passively learn strategies for active causal experimentation and exploitation. Awesome. But those were some pretty toy environments. So the thing I'm going to try to do next is to move to some slightly more complex tasks and introduce this idea of how explanations could help. To do this, I'm going to do a bit of a little parenthetical divergence because we actually introduced these tasks in a prior work with reinforcement learning agents where we looked at how explanations could support learning relational and causal structure. So now I'm going to tell you about the tasks we used there. The motivation for that work is that human learning is very pedagogical and it focuses on explanation, of course. So we talk to each other a lot about the things that we're learning. And when you get an exam, you often don't just get feedback that says you did well on this, you did poorly on this, but you also get an explanation of what you did well or poorly on each question. And so we wanted to ask if, right, and so this is more informative than reinforcement learning rewards alone. And we wanted to ask if it could help agents as well. And to do this, we set up a task that we thought would be hard to learn from rewards alone, which are these odd one out tasks. So the way these tasks work is we show agents, or we put agents in a situation where there's a variety of objects. We ask the agent to find the object that's unique, or that's what the agent has to learn how to do. But we make this task a little bit hard for the agents. So for example, here the unique object is the green one. We make this task a little bit hard for the agents by setting up the objects in such a way that if you look at any proper subset of the objects, you can't figure out what the right answer is. So for example, if you look at just these three objects, you might think this one is unique because of its shape, or this one is unique because of its size, or this one is unique because of its color, right? So you don't know which one of them is the answer. And because you have to consider all of the objects and all their relations in order to figure out which object is unique, this is a pretty hard problem to learn from reward alone. So what we want to ask is whether predicting explanations during the training process, like you might get from a teacher, would help the agent to learn. And so the way we set this up is that when the agent takes a action, like it chooses one of the objects, predicts what a teacher would say about that action, and in addition to the regular reinforcement learning signals, it also learns from the match or difference between what it predicts and what the teacher actually says. And the way we set this up in the agent is just we hang another head off of the agent, which predicts the explanations in text, and it learns by a cross-entropy loss, just like a language model, from the difference between what it predicts and what the teacher actually says. And the idea is that this will hopefully give the agent better representations in its transformer and in its encoders of the world and its structure and what it's supposed to be doing. OK, and we found in this previous RL work that indeed these kinds of explanations helped agents to learn. So when we situated the tasks in a simpler 2D environment, agents with explanations do quite well. Agents without explanations learn something. And you can check out the paper if you're interested in what that something is. But in a more complex 3D environment that's more partially observable, you really need explanations to do well at this task at all. OK, end of the parenthetical. Back to our scheduled program. So in that paper, we also proposed this more complex intervention task, which I'm not going to explain in full detail for the sake of time. But it's basically the same structure as the tasks I showed you earlier. So there's some latent causal graph that changes on every episode. The agent gets to do some kinds of experiments on different trials in order to figure out what that causal graph is, except now it's grounded in this more complex relations between objects setting. Then we give it a final trial where there's different objects, and it has to choose one that corresponds to exploiting that latent causal graph, and it's rewarded, or we assess it by how well it does at that task. And of course, these tasks are not just in that simple setting, but the grounded is a slightly more complex 2D environment, which is partially observable, and so on. Just as in the prior experiments, we train the agent via BC on passive data from an expert, which is near optimal at trying to discover the latent structure and then use it to achieve reward. Not perfectly optimal, but close. And we find that in this setting too, BC agents are able to generalize these tasks from passive data. We do a couple of different train test splits, and one of them is harder than the other. But in either case, the agents are doing very, very well at these tasks from passive learning. And explanations also help with that learning if we train the agents to predict explanations during training. But the interesting thing is, so explanations here are in pink. Agents trained without explanations are in bluish. And what you can see is that there's actually not as big a gap here as there was for the reinforcement learning agents. I think the reason for that is that actually there's some advantage that you get from observing the expert policy here that gives away some info about the task that otherwise would be hard to discover from reward alone. OK, cool. But explanations can do more than just help to learn something a bit. They can actually help to learn something in a case where it would be impossible to learn it from the data alone, and that's in the case where the features are totally confounded. So to show this, we trained agents in a slightly different setting where the task is a little bit simpler. We just put the agent in a situation where there's 4 different objects, and one of them is unique in 3 different ways. It's unique in color and texture and shape. And we're going to train the agent to pick up the unique object. This is a relatively easy task for the agents to learn. They learn it quite quickly. And then we're going to give the agent a sort of tricky test where we put it in a situation where different objects are unique in different ways. So there's one object that has unique color, one that has unique texture, and one that has unique shape, one that's just a pure distractor. And we're going to ask, which object is the agent going to choose, and can we change that choice via explanations? That is, if there's some latent causal graph here that we know, can we shape the agent's inferences based on explanations? So to do that, we do this between agents manipulation, where we train different agents with different kinds of explanations about what's going on in this task. So when the agent makes a choice like this, some agents get color explanations, like this is incorrect because other objects have this are purple. Some get shape explanations, and some get texture explanations. What we find is just doing this kind of explanation-based training is sufficient, even though the trajectory data are totally ambiguous, to push around what the agent will do in the out-of-distribution test setting. So if you look at the purple curve, that's showing how often the agents that are trained to explain in terms of color choose the unique color object. Nearly 100% of the time, blue is with shape and green is with texture. In each case, just the explanations are forcing the agents to generalize in different ways. And the reason, I think, is just that features that are explained become salient to the agent. They're really driving the agent's representations because it's getting all this language input about them, or it's having to predict all this language input about them. And therefore, those are the features that the agent learns to use to generalize. All right, so explanations can help to shape generalization out of distribution. Any questions so far? Awesome. So, all right. That was a bunch of experiments in more controlled settings where we knew what was in train and test. But I started this talk with some motivation about actual language models. And now I'd like to return to talking about them for just a second. So what we did in this paper with actual language models is we wanted to test them on the same kind of causal tasks, causal strategies that we explored with the agents. And to do this, we took a pure language model, Chinchilla 70B. And we took the odd one out interventions task, and we turned it into a language task that we augmented with various explanations. So basically, we gave this language model a magic wand and let it interact with some objects. And the way we did this is we turned the observations of the task into text. So where the agent would actually see some pixel inputs, we just put in text inputs describing the objects. And we turn the actions into text too. So these bold things here are actions that the agent gets to take, the language model gets to choose. And then we get feedback from the environment in terms of rewards. And we augmented this prompt with explanations of what's going on in each setting, and also with reasoning traces, sort of like chain of thought. And the idea is that we're going to give the model a prompt, and we're going to give it explanations and reasoning traces within that prompt. Then we're going to test it on a new episode. And in that new episode, the model itself will have to generate explanations of what's going on and reasoning traces. So to make that a little more concrete, we give the model a 4-shot prompt where it gets expert choices and explanations on some causal structures while holding out others. Then we're going to test its performance to generalize to new instantiations of the same structures that occurred in the prompt, or to new causal structures that didn't occur in the prompt. So first, I'm going to show you the same causal structures that occurred in the prompt. And here, both a prompt without explanations and one with explanations and reasoning both do pretty well. So the language models can just get the task for the same structures that are observed in the prompt. But if you test the causal structures that didn't occur in the prompt, there you see a big advantage of the models that were prompted with explanations and reasoning traces, suggesting that having this sort of abstraction of the causal structure made explicit in the prompt and giving the model the chance to generate it at test time allows the model to generalize in a way that it could not without that. OK, cool. So that I sped through this talk much faster than I thought I would, which is good. We'll have some time for discussion. With that, I want to wrap up. And to do that, I want to raise one more point that I think is quite interesting about this, and I haven't actually talked about before, so I'm excited to hear your thoughts on it. I think that one of the things that's underrated about language models, and that's very important to these final results, is the fact that they bridge across different levels of abstraction in a unified space. So in the text input and output space, and also in the internal representation space of these models, they can process in a parallel way things that are observations about the world, causal relationships and explicit statements about those, interventions on the world, broader explanations, and higher level causal principles, right? And this is a property that is quite unique to language models as sort of just something that you throw all the text on the internet at, relative to more structured cognitive models like, classical causal DAG models or sort of neurosymbolic models and many other models like that. So I think this is actually this ability to connect different levels of abstraction in a shared representational space actually enables more flexible kinds of learning and reasoning that you couldn't do if you were sort of restricting the way the model could relate between these things. And I think it's quite important because I think humans are able to do this quite a lot, that this is a really fundamentally human behavior, whether in the kinds of metaphors we use to make abstract concepts more concrete to us, or in the ways we think about abstract concepts like mathematical reasoning, where we often relate between different levels of abstraction. So I think flexibly linking across levels of abstraction will be key to building systems that approximate higher level cognition. With that, I want to summarize. So what I tried to argue in this talk is that it's possible for a system to learn generalizable causal strategies from passive data. Explanations can support causal learning. This is relevant to understanding language models, BC agents, and other systems' causal capabilities. And I think it's enabled in part because of this fact that language models bridge levels of abstraction in a shared space. I do want to highlight some caveats because otherwise I know that everybody in the audience is going to point them out to me. So I want to kind of preempt that. First, this existence proof doesn't mean passive learning is as good as active learning. There's a ton of neuroscience and cognitive science and machine learning literature that shows that's not, including this really fascinating experiment with the cats, which you should look up if you haven't seen it before. Nor that confounding is not a problem. Obviously it is, even for us. And of course, there's a lot of bad data on the internet, which may be fundamentally hampering these systems because, of course, the systems we trained were trained on nearly optimal expert data. The real internet has a bunch of trash on it and a bunch of bad explanations, and maybe that makes it harder for these systems to learn. For Sherry's sake, here are some broader questions. So first of all, I think this question of how we can make intelligent systems flexibly bridge levels of abstraction is quite an interesting one. And I think language models are probably only one step along the way to that. I don't think they're the end of the line. But I think it raises a more fundamental question, which I'm bringing up just because we're at the Simons Institute, which is, how can we formalize theories of intelligence without making overly restrictive assumptions about the structure of intelligence, like what things are relating to what other things? Because the reason that a lot of the prior work has suggested that language models can't learn about causal structures from just learning from data is because of the assumptions, the restrictive assumptions it imposes on what data are and what they can say about the world. And if you change those assumptions, it fundamentally changes the conclusions you draw from that theory. So I think this highlights the challenge of making good theories that don't make bad assumptions about the world. I think our results are also interesting from a philosophical perspective of agency because you get this thing that seems like sort of like generalizable goal-directed behavior from purely observing in some sense what other people have done, which is pretty interesting. Also, of course, from a cognitive perspective, I wish Allison were here, but she's seen me talk about some of these things before. But it raises the question of whether representations that are learned from more human-like, actually some interaction, but also passively observing what parents do, for example, would be sufficient for human-like causal understanding, or whether some stronger inductive biases are needed. And finally, as I noted earlier, active learning can be quite important and a lot more efficient than passive learning. So this raises the question of where does active learning matter for language models? And a couple of candidates that you might think, either from prior literature or from some empirical results, is that it might matter for robustness to distribution shift that's generated when the model starts to interact, or it might matter for learning social things like pragmatics that are maybe much easier to learn if you're actually interacting with another human than if you're just sort of learning from imitating what others are doing. So with that, I want to thank you. This is the paper if you're interested, and I want to thank my co-authors, Stephanie, Ishida, Andrew, and Jane. Thanks, y'all, for listening. Happy to take any questions.
Thanks, really interesting. I was interested in the discussion at the beginning where you distinguished observation from passive learning in your 2x2 matrix and said, yeah, well, you can learn about causal structure by passive learning, but you still X'd out the whole observation column. And on the face of it, the same considerations that you were giving seem to suggest, well, you can learn causal structure through observation, for example, by observing people's interventions. I can watch someone perform an experiment. I can watch them on TV. You maybe what's going on in that case is, well, at least it's an intervention involving an agent or something. But I don't know. Prima facie, you could also do that watching a robot perform the experiment, watching a whole bunch of switches and pulleys perform an experiment. So at this point, I get I start to lose track on what is the key thing to learning about causal structure.
Yeah, so I'm glad you brought that up. I mean, I think I generally agree with this, and I think that the ability to identify something as an observation, as an intervention, is the key point, and it's often quite explicitly highlighted in internet data to some extent. It's very explicitly highlighted to these agents because of the structure of the data we're training them on. It may not always be so clear in the broader range of settings. But I think this also kind of relates to some of the philosophical issues with how Pearl defines causality and how that actually maps onto the sort of messy stuff that is the real world, which is that the notion of intervention, in something as complex as the real world, is not entirely well defined. I know Pearl has tried to grapple with this a bit, but for example, if your abstract variables are like people's, variables about people's health, like their blood pressure or something, when you do an intervention on one of those variables, it's never a clean intervention. It's also doing other things, like you're causing their liver to process some more medicine and things like that. And so it becomes quite hard to say what an intervention even is in a clean sense, and to know whether those interventions correspond to are telling you something about the causal structures you really think they are. And so I think these kind of issues come up both in the case that you're sort of observing what other people are doing, but also just in the case that the world is messy and your interventions are not very clean themselves.
One way to think about intervention is it's something that doesn't really have a relevant causal history. It's kind of out of the blue, in a really idealized way. It happens non-deterministically, or at least it's not under the causal control of any of the other relevant variables. But then to know something's an intervention, you kind of have to know something about the causal structure. So it gets a bit circular.
Yeah, totally. So while the next person's getting the mic, just to riff off that, I think one of the interesting things about language and explanations as a way of presenting causal structures, as opposed to causal graphs, is that maybe language, because of its inherent ambiguity and also because of its greater flexibility, maybe leaves more possibilities open for the causal structures to be incomplete that are expressed in language, and maybe makes it easier to present something about some sort of causal information without it sort of conveying the idea that that is all the causal structure out there in the world.
Yeah, hi. Thanks. Megan Peters, I'm at Irvine. I have a question. There was something, I think it was section 3 that you said that struck me, which is that one of the things that the explanations might be doing is bringing certain features into salient, like making them more salient for the model, and then it uses those. So I was wondering if you'd thought about, as a control, creating explanations that are completely matched on surface level statistics, but totally wrong. And so then they can match that salience induction, but like a human being would either eventually learn to ignore them or might be really tripped up by them, and kind of see whether it's just the salience or whether it's actually the explanation that's doing the heavy lifting.
Yeah, that's a great question. So we did similar experiments in the reinforcement learning work, and in that context, we ran a bunch of control conditions, which we didn't run here. But I think the most relevant one of them was that you provide explanations that are could be given in the current situation, but aren't actually responding to the agent's actions. And that's something that's makes a bit more sense maybe in the RL setting, but we could do it here too. Just the explanations don't correspond to the expert's actions, but they are relevant to the particular scene. And in that context, we saw there was very little effect of the explanations. So I don't have good controls in this work, but in the prior work, we did something similar with the RL agents, and we did see that it was pretty important that the explanations be somehow very relevant to what the action actually was that was being explained.
Okay, thanks.
So I have a question kind of thinking about how one might theoretically formulate this kind of question about interventions and so forth. So it feels like maybe on the one extreme, there is purely observational IID data. So you're just observing correlations, and you press a button, you get another random sample from the distribution, and that feels very just correlational. On the other extreme, there's kind of the actual ability to interact with the world and, do things and so forth. But then there's this kind of in the middle where it's not IAD, it's just not you doing it, but maybe like the talk we saw with watching 24-hour video, somebody's doing, there are things happening, things caused by other, so there is causation happening, and somehow that this, even if it's not you. So I guess I'm in trying to think of how one might theoretically formulate. I wonder if maybe one could extract some things that you would need that maybe it doesn't have to be you doing the changes, but something that moves away from just the pure IID setting.
Yeah, I mean, I think this very much relates to David's question, which is like about how you identify the interventions, right? So I think this kind of, we can make this distinction like we would do in sort of like cognitive experiments, for example, between like sort of like just like an experiment as such, like longitudinal data and actual like like correlation, longitudinal data and interventional data. And the longitudinal data is maybe getting a bit closer to the setting you're talking about, where it's like, oh, I observe how someone's like, working memory capacity and some other cognitive variable changes over time, and I see that like working memory capacity at time 1 is related to ability to I don't know, number of words learned at time 2 or something. And so that maybe like hints at some underlying causal structure there, but unless you know something about where those time 1 things came from, there could be lots of other sort of like confounding factors that are driving that. And I think it's similar in the videos, right? Like some things you might be able to see that a person is doing. Some things might be sort of like being driven by something entirely different, but they happen to be correlated with what the person is doing. So I think, it depends on the extent to which you can identify from those data what sort of the interventions are that's driving that. But in general, I agree that like you should be able to learn strictly more from the longitudinal setting than you can from the IID setting, but you should be able to learn. In some cases, you need to intervene to learn all you can.
Lucy Cheek, Cambridge. Really nice talk. Thank you. So it might be that I'm kind of taking an overly simplified interpretation of the examples that you've given, but it seems to me that quite a lot of the tasks you've got are sort of what I would call in animal stuff as observational reinforcement learning. So it's kind of learning what gets you rewarded. Whereas to me, a lot of like causal learning would be about learning the fundamental structure, and then that's tested not by doing the same thing again to see if you get rewarded or not doing the same thing as someone else did, but to extrapolate a new thing based on your understanding of the causal relations. So do you think that's a meaningful distinction? Yeah.
So I guess like the meta-learning type tasks we use have kind of 2 levels of learning, and maybe I should have just like unpacked them a little more, because I think at the higher level, the agent is doing something that's more like the more complex case. So just to clarify that a little bit more, so within each episode, the agent is doing learning that kind of corresponds to what you're saying. It's doing learning of like identify what's rewarding in this particular situation, and then use that to achieve some goal, right? But identify how things work in this particular situation, use that to achieve some goal. There's 2 points I want to make. The first is that in the causal DAG experiments, there's the notion of reward is not clear until you get the goal, which happens after the exploration phase. So basically, like if the goal were maximize node E, that might require a different intervention than if it's maximize node C, for example, right? So it's not that straightforward in that sense, but it's also the case that like at the higher level timescale, what the agent is actually learning to do is that full experimentation to exploitation phase, which is again sort of like adding another level of relations on top of that, which is like, okay, it's at each episode, it has to experiment, figure out what's going on, and then figure out how to exploit that. And that is where we're doing the train test split, where there's structures at test time that are never observed at training time. And so that's probably in some sense, the more interesting version of the fact that the agents are learning something more complex than just figuring out what's rewarding and then exploiting that.
I was going to channel Allison, who had to go do some caregiving to her grandson. But I think maybe you've already talked with her about this, because this is kind of a follow-up on Avram. She has, I think you've talked, and she has this whole empowerment idea of that, that one, maybe an intrinsic reason or motivation for learning is that being able to manipulate the world. And it's kind of like a form of curiosity learning. And I'm wondering, like how, and another thing, how it's related to Avram is that she has this theory that, you start learning by doing your own manipulation in the world, and then you learn some causal structures that way. And then later you grow up to be able to see other people manipulating the world and learn from that. And then finally you get to the point that you can just look at that, how the stars move and the constellations move and kind of infer something causal about how the universe works. So it's like the three stages of causal learning. And I'm just wondering, how do you think about the fact that you can do all this passive learning just from like causally existing data with this whole idea of hers?
Yeah, that's a great question. So something Alice and I talked about when I talked to her about this is actually the fact that her classic Blickett experiments, not necessarily all her Blickett experiments, but the classic ones are actually very much like this setting in the sense that the kids don't do the initial experiments that tell them what the causal structure of the Blickett detector is. They just observe the sort of confederate of the experimenters putting some things on the Blickett detector and making it light up or not light up. And it's from that observation of someone else's interventions that they learn about the causal structure of the Blickett detector, which is then tested in these sort of more active settings. So I think there's a very close analog to this kind of learning and the things that kids are doing, at least by the ages that they pass the Blickett detector experiments. The question of whether, I think this is related too to the questions about identifying the interventions, because I think there's a sense in which we're making the problem easier for the agent here because the interventions are marked in the sense that they're sort of consistently driving some change in the environment. Whereas like for the child, there's a little bit more perspective taking or something probably that has to go on for them to realize that the person putting the objects on the Blickett detector is some sort of like driving the causal change in the world. And that might be something that they learn from sort of like interacting with their toys, where they push it, they learn that like interacting with something and making it like light up or make noise is sort of like a causal effect that's driven by that interaction. And I guess like in the simplifying assumptions we've made, we've kind of like gotten rid of that. But for the language models themselves, there is some more of that problem coming in. I haven't fully tried to explain how they're crossing that boundary, but I think it's a really interesting question that could probably be explored with relatively similar approaches.
Hello, Adam Shai. Thanks for the very interesting talk. I forget if it was in section 1 or 2, but in the experiments with the DAGs, if I understood it correctly, your kind of main analysis for saying that these models had learned the causal structure was behavioral, and in particular, kind of compared their behavior with that of an optimal expert that presumably used the causal structure. I'm wondering if conceptually you think there's a distinction between kind of behaviorally acting as if one has a causal model that they can manipulate using do calculus or whatever, and actually having one inside, and then kind of relatedly, have you done any work or do you know of any work that actually kind of looks for the structure inside of the model internals?
Yeah, that's a great question. I mean, I'd say the closest work I know of is actually probably Jacob's work that he talked about yesterday, sort of looking for world model-like things within language model representations. I haven't personally done representation analysis work on these particular models to try to figure out whether they have DAG-like representations. And it's partly actually because I'm I'm quite certain that we would find that you can linearly decode DAG structure like things from the representations of these models. And I'm not sure how much that would tell us about what the model is actually doing. Like I think, to some extent, linear readout is too flexible a measure of what the model is actually doing. So yeah, it's mostly because of that concern, and also just because I'm lazy that I haven't actually done some representation analysis here. But I think the question of like, behavioral analysis versus what the system's actually doing is quite an interesting one. I guess that I definitely think there's a distinction there, which is important to make. But I guess as someone who's mostly in past lives been a cognitive scientist, I tend to think of it as something that could still be probed ultimately with behavioral kinds of analyses, whether it's through sort of like more like self-report type things that you could do with language models, even if you can't do them with these agents, or even through sort of like posing careful tests that try to tease apart the possibilities. And something I should say about the tests here is that we actually design them quite carefully in that sense, so that like it should be very hard to get the correct answer unless the system is using causal methods. And that's actually why you see more separation between the sort of correlational and heuristic methods and the expert method in the test conditions, is because the test conditions are more stringently constructed to make those sort of those methods perform more differently. So like I tend to think about these things more often in terms of like designing careful behavioral experiments that allow us to tease these things apart. But analyzing it in terms of the representations and trying to figure out what's going on there is a very interesting method, an important method as well. I have a lot more to say about that because I'm quite interested in the philosophy of representation and computation too, but that's a whole other topic.
Thanks.
Thank you for the talk. I was wondering, so for all of the, using RL or LMs to sort of infer the DAGs experiment, am I right in assuming that the nodes are predefined, like there are only those 5 nodes or 3 nodes? Then you're really just inferring the edges, not the whole DAG. And I think it's more of an open challenge to both communities like language modeling and RL to figure out what are the critical steps, what are the critical nodes. How much do you think passive learning can do that?
Great question. So I'm glad you asked. This is actually one of the reasons that I liked having the experiments that I talked about in the next section, because the nice thing about these experiments is that sorry, let me say first that you're right. The nodes are predefined in the DAG tasks and in the language model inputs as well. They're kind of predefined because language discretizes things in a nice way, at least the way we prompted these models. But for the agents in these tasks, they're really getting these sort of pixel inputs where the things that are nodes in the graph are like features that are properties of like subsets of pixels in the image that the model needs to learn entirely from the combination of the sort of like behavioral signals, the things that it's imitating from the expert, and the explanations that it's imitating. So in this case, I think that the system is passively learning some from like more raw inputs, just these pixel arrays, to figure out what the latent nodes are that it's using to solve the problem. But for language models, maybe it's a little easier, and maybe this learning of the mapping from pixels to the abstract variables is hard in general, which is why in a lot of the talks we've seen earlier, for example, the perception talk, we see that these models are not always super great at solving very basic things, or the visual analogies talk and so on. So yeah, I think that's a very important problem. And it's, I guess, one of the reasons that I personally think that the Perl-like causal literature is missing a big part of what actually makes intelligence hard, because I think the mapping into that abstract space is a lot of the hard part. And it's a lot of the thing that's still hard for current models.
Thanks. So it makes a lot of sense to have a very simple DAG model, like the synthetic data to kind of understand. But coming from the medical world, then things are a lot more murky, right? So there's a definition from Nancy Cartwright saying that causality is you have enough evidence to act. So if you take that view, then how would we test that? A lot of people are using ChatGPT for medical advices. And how would you go towards showing something, whether the ChatGPT is getting the right causal recommendation for people to act, say, to do something, to see a doctor? So can you just think aloud on that? And also multiple explanations, I think, will be at play instead of just for this, clearly, hopefully there's one version explanation. But if I go to something like medical conditions, you're going to have different doctors who may not end up with the same action, have surgery, but actually people will have different explanations why they would do a surgery, which is intervention.
Yeah, so a bunch of fascinating questions there. On the medical side, I mean, I think the simple answer is that we should assess something like using ChatGPT in medical applications the way we assess any medical thing, which is ideally with randomized controlled trials if we can, because I think that's probably the best measure of, is this system actually helping or harming? And I think that like both humans and these models will learn some correlational things and some causal things and some causal things that are incorrect, but still in a lot of cases help us to make accurate enough inferences. You know, medicine is an imperfect field. And so that's why I would say like test it empirically and see if it helps with some doctors intervening to make sure that you're not doing crazy things. And that's probably the how we should decide whether a system should be used or not. I'll let you respond, but I do want to respond to this multiple explanations thing too. I think this is a super fascinating issue because actually the same thing is true in a lot of the cognitive literature and explanations. People talk about how pragmatic they are in the sense that they're very like directed to the dyadic interaction, right? Like if I'm explaining something to you, I'm going to give a very different explanation than if I'm explaining it to a 5-year-old, and that's a very different explanation than if I'm explaining it to an adult who's happens to be naive about machine learning, right? And so there's a lot of explanation that is like both, you know, explanation is driven by the communicative context, and that is very different in any particular situation where you're giving an explanation. It's driven by the sort of like latent inferences that both the explainer and the explainee are making. And that is a feature that's not at all modeled in this work, but I think it's a very interesting feature of explanation that is needed for us to help language models use explanations as a learning signal, because human explanations are very driven by context.
Yeah, I agree completely. But I was also meaning that actually there might be mechanistic different interpretations for a particular action, right? So you have these different levels. I think it might help you for complex task to entertain these multiple mechanistic interpretations to get better performance.
Yeah, so I think that's totally possible. I mean, I think to some extent the language modeling objectives have to do this in the sense that they're trying to match the distribution of responses. So if they're, you know, if it is the case that it's not the case in these environments, but for language models learning from text data on the internet, if there would be the same action that's presented, that could be presented with different explanations of why it's valid, like because people would give different explanations to a child or an adult or on different forums or whatever, or because different doctors would have a different mechanistic story about what's going on in a particular case. The models should, if they learn the task well enough, they should learn to model that distribution and assign some probability to each of the different answers that could be given. And you know, in the cases where we can quantify this more explicitly, we can see that they are to some extent matching the distribution of possible explanations. So I think there will be some of that learning going on already, but it's possible it would be useful to take advantage of it more explicitly in various ways. Totally.
Yeah, just come back to your clinical trial. I think a lot of what you do might be interesting to design the clinical trial, right? How do you, what you're going to compare? That I think it's probably not just clinical trial, but also understand how to ask questions.
Yeah, that is a very good point.
Thanks.
Why don't you ask the last question, and then in the meantime, I'll have all the people who spoke, all the speakers, grab a chair and come up.
So I wanted to come back to what Yoav was saying in his talk about sort of praising the language model in order to make it better at the task that it was doing. Like, you know, so far we've seen the demonstrations getting generated by a fixed experimentation policy. What other machinery do you think is needed to actually also get sort of better, you know, not just at the sort of doing the right thing after you've run the experiments, but at designing the experiments themselves? And is that the sort of thing where you can just, you know, do reward condition behavior cloning or what?
Yeah, that's a great question. I mean, we ran a very simple analog to that with the agents, which was not the full decision policy, but just a setting where there's kind of like, you don't get time to perform all the experiments, but you get some cues that you could think of as like prior knowledge about what experiments might be relevant. And the agents do indeed learn to sort of like take account of those. And that's, you know, a little bit closer to what you would have in a real world situation. But I think the question of how you get an agent to learn to perform more optimal experiments by experimenting is quite an interesting one. And you know, I'm sure if you throw RL at it with enough experience, it'll learn it. But
well, yeah, no, but if you want to do that observationally,
If you want to do that observation. I mean, I think in principle, like based on the experiments, for example, with the prior knowledge stuff that I didn't tell you about today, I think that the systems would be able to learn it observationally. But again, it takes quite a lot of data to do it. And like, this is the kind of thing where I think that explanations should help. And for humans learning about these things, explanations are quite important into understanding like how we do experiments, right? So I think that would be the direction to go into, like look at generating good explanations and sort of like curating the data more. But yeah, I haven't thought about it that much. It's an interesting question though.
Thank you, Andrew.
Thanks.